Hello everybody, here I am with the video of homework 4. Now this is again a homework for a teamwork here. So you will be working in teams again, as it was the case for homework 3. Now this homework focuses on the frequency domain and state space methods. We have a spring mass damper system which has a signal order transfer function. These numerical values depend on your team number. You're given a rise time and overshoot criteria, so that we will be designing controllers that should meet these criteria. And we have some identities given. First of all, we have the rise time here, an approximate equation for the rise time, and then we have an equation for the phase margin. So using both these you can calculate basically zeta and omega n, and then you can so basically we have overshoot, rise time, so you will be calculating rise time, phase margin with ease. So our first question is concerned with the frequency domain approach. We will be designing a PI controller here. So the PI controller should satisfy the given condition here in the closed loop. So we have the PI controller, the system, a unit feedback closed loop, and then we have the transfer function of that. Now that transfer function should satisfy this 1 and minus 180 degrees point on the Bode diagram. So you have to plot the Bode diagram of the open loop, and then you will be trying to come up with a PI controller that satisfies this here. Here we have omega n, and then you will be trying to use this identity here. Here we have given you an extra identity which should help you out in designing the PI controller. So this might take a little bit of thinking and brainstorming, because this is not a usual frequency domain synthesis question, because that would have been not that informative for you. So hopefully that this question will give you a better opportunity about thinking about the frequency domain approach, what it really tries to accomplish here. So if you figure out A, which heavily relies on this identity here given, if you figure out A, B will be very simple, because it's the same idea. The only difference here is that we are not looking basically at the closed loop stability point. We are looking at the closed loop design. So we are trying to match the criteria that is given to us. So basically, if you figure out A, B will be very easy. So, and then we have C, where we are asking you for the phase margin of the system, which is straightforward in this case. But if this phase margin happens to be infinitely large, then what should be the alteration of the system, or how should we modify the system so that we have a finite phase margin? And you should provide an example here. That example should give a numerical result. So you should show how that numerically the modification should be done, and what the phase margin becomes. So ABC is more concerned with the frequency domain approach, and as I've told you, A and B is more about brainstorming on using the Bode diagram and getting a better view of the frequency domain synthesis method. Now in the upcoming questions, we are dealing with the state space approach. Now in D, the question is to give the transition from the transfer function in the Laplace domain to the state variables. You should do that step by step, which is straightforward again. And then you should give the representation in the matrix form. So we've worked out x1, x2, x up to xn, and then you should give the matrix representation. And then using that state space model, what you should do is you should come up with a with an example equivalent spring mass damper system, and then calculate the spring coefficient, the mass, and the damper coefficient. So this should give you an idea on how a spring mass damper system has its model defined in state space and how it's relating to the real world. Now in E, we have a question which asks us to design a state feedback controller, which is again straightforward, by the way, because we had this in our last lecture, or it will be in the last lecture in your lecture notes. So calculating a phase margin, designing the state feedback controller. The only thing is that you should provide all the steps of your design, just not the answer itself. There should be a step-by-step explanation in your report. That's the only key here. And in F, we have a state space model that is augmented as the following here. So here we are adding a new state to the system. So we had a model that was representing the exact same transfer function that we had. And what we're doing here is we're augmenting or adding another state that has a special meaning for us. And this state tries to calculate or take into account the error that is defined between the reference and your output. So this is basically r minus y here. This q dot is equal to r minus y. So this augmentation should make a difference in the control strategy. And the aim here is that you design a state feedback controller that has this that tries to meet these rise time and overshoot requirements, as it was the case in E, but this will work a bit different because this is a higher order augmented state space model. And last but not least, we have a question where we ask you to design a Lindbergh observer, which should be designed for the augmented system. So in case of a lack of measurement for the states that are necessary in order to apply the state feedback control, we opt for the Lindbergh observer that uses its output and the output of the system, the difference as a dynamic and an error dynamic on its own. If that error dynamic is stable, then we are basically estimating the states. So the question here is to design a Lindbergh observer and then feedback constructing the feedback law using the states or the state estimations of the Lindbergh observer. And of course, since this is a report, you should compare the results of B, E, and F. In B, we had this design using the frequency method. There was a PI controller. In E, we had this state feedback controller design that was not augmented, that was designed for the original system. And then we have F, where we have the augmented system that has an integrator in it and the state feedback for that. So you should compare them on their pros and cons and should provide the results. So as you can see, the due date here is the June 20th, so which means that there is a slightly tighter window in order to prepare the report, work on this homework, and submit it. But keep also in mind that some of these questions are pretty straightforward. If you use your lecture notes or laboratory notes or textbooks, then some of the designs are available already. So using the Ackermann formula and designing a state feedback for E, F, and G, they're pretty much not that much hard, since you already know how to apply the design step by step for E, F, and G. And we can also use D and C. So basically all these questions are straightforward. You know what to do, you just have to do it and explain it step by step. The struggle here might be on this part, considering the frequency domain, but this should also help you out in trying to understand the basic philosophy of the frequency domain approaches. So Hope that this homework will be useful, and hope that you will have some fun during the homework, because essentially what you have to do here is to just use your notes and try to carry out the designs that are explained. So hope that you will enjoy this homework. So good luck.